Hello, welcome to NPTEL online certification course on Introduction to Application of AI to Robotics. Today we are going to see Newton-Euler's equation example. So, in the last lecture we have seen the derivation of the Newton-Euler equation, okay, and today I want to go through one simplest example of two-link planar manipulator, the simplest possible type, and I would like you to take pen and paper and try to do this example that will help you to get a deeper insight of the problem. I expect that by the end of this lecture, you will be able to solve a dynamic manipulator problem analytically. Okay. So, here basically I am going to take the 2 degree of freedom planar manipulator with point mass, and we are going to get the dynamic equation. And as you know, the process comprises of the two steps basically. One is what we do as the outward iteration, where we calculate the velocities and accelerations, and then the inertial forces and moments, and then we have the inward iterations, okay, through which we calculate, coming from the last link to the first link, we calculate the joint torque. Okay. So, let us take this example. This is the simplest example possible. Suppose this is a two-link manipulator, and this has got the point mass. There is a point mass at say M1 here, M1 and M2. I am taking point mass assumption so that our inertia tensor, it is a null matrix, okay. Yeah, and there is one more change here which is going to be there because of this simplified assumption, and that is that at the tip, the center of mass of the first link is going to be at the end of the link over here. Similarly, the center of mass for the second link is going to be at the end of the second link. So, these are the two simplifications which will be happening because of the point mass assumption. Okay. So, here first to begin with, let us assign the frames to the links. So, say my x0, y0 is my inertial frame which is attached to the base of the link. This one is my x1 cap, y1 cap is the frame attached at the starting of the first link, and similarly x2 cap and y2 cap are put in over at the beginning of the second link, and x3 cap, y3 cap is at the tip of this manipulator arm. Okay. So, this is there, these are point mass M1 and M2 here, these are length L1 and L2. Say the joint angle here is theta 1, that is the angle between x0 cap and x1 cap, and theta 2, that is the angle between x1 cap and x2 cap. So, this is my direction of x1 cap. Okay. So, what is known here, that is the location of the CG frame expressed in terms of the frame 1. This is what I said. Similarly, location of the CG frame for the second, that is going to be over here. And then as I said, point mass assumption, the inertia tensor written at the center of mass for each link is a null matrix, 0 matrix over here. And let us do the assumption that there are no external forces or moments acting at the tip. So, we get this condition from that, and base of the robot is not rotating. So, the omega 0 and omega 0 derivative, they are 0, and to include gravity force, as I have discussed in the previous class, we can take the base to have acceleration g in the positive y0 cap direction. Okay. So, the rotation between successive link frame we can define. So, this is what we have seen earlier, the rotation matrix for the description of I plus 1th frame with respect to ith frame is this one. Okay. Similarly, description of ith frame with respect to I plus 1th frame is simply the transpose of this one. So, the transpose of this one is this one. Okay. So, now let us begin our process. Okay. So, as per the Newton-Euler algorithm, first we have to carry out the outward iteration. Okay, so outward iteration for link 1 we can carry out, and that I can do by putting I is equal to 0 in the recursive equation. So, the recursive equation for the angular velocity propagation is this one, okay, that is the angular velocity of I plus 1th link expressed in terms of I plus 1th link is equal to the angular velocity of the previous link, which is this one, okay, and this is expressed in terms of I plus 1th frame, and this is that I plus 1th joint velocity. Okay, so let us put I is equal to 0 in this one. So, I get this equation omega 1 and this is omega 0 velocity plus theta 1 dot and all expressed in terms of the frame 1. Okay, this is already expressed in terms of the frame 1. So, we assumed that this value is 0. Okay, the base is not rotating. So, there is not going to be any contribution from this term, and this term, as we have seen in our discussion earlier, this is nothing but that z component is existing here. So, this value is going to be 0 0 and theta 1 dot. So, this is omega 1 1, that is the angular velocity of the first link expressed in terms of the first link. Okay, let us find out the angular acceleration. Okay, so for that, this is the recursive equation for the angular acceleration. Okay, that is angular acceleration of I plus 1th link, okay, is equal to the angular acceleration of the ith link plus that joint acceleration, and then you are going to have a cross term involving these two terms. Okay, so we have seen all these involving this omega II into you are going to have that joint velocity term. Okay, so this is the cross term which comes. So, I can put I is equal to 0 here in order to get the acceleration of the first link. So, with this, these are the terms which we are getting, and again this one we have already assumed that this is going to be 0, this term we have assumed to be going to be 0. So, the contribution from only this one will be coming, and that will be 0 0 theta 1 double dot. Okay. So, this is how we find out the angular velocity and angular acceleration of the first link. Okay. Now, let us find out the linear acceleration or translational acceleration. So, for that, this is the general expression which says that the translational acceleration of the origin of the I plus 1th frame expressed in terms of I plus 1th frame, okay, this is going to be equal to what? This term, that is the angular acceleration of ith frame, okay, plus there is a omega cross this one term is going to be there, and then you have a double cross term is going to be here. Okay. So, this is what we have seen. So, if I put I is equal to 0 over here, so this is what I get 0 to 1 omega 0 0 cross P 1 0 plus omega 0 0 cross omega 0 0 cross, you have P 1 0 plus V 0 0. Okay. So, again this term we have assumed to be 0, this term also we have assumed to be 0, this is also 0. Okay, so again here what contribution I am going to get is here. Now, in this one we are everything is expressed in terms of the 0th frame. Okay, so I use a rotation matrix here in order to express it in terms of the first frame. Okay, so this is my R0 with respect to 1. Okay, so this is what going to be, and this one I got from this equation. Okay. So, this equation, from this equation by substituting I is equal to 0, I can get this one. Okay. So, I substitute over that, and this acceleration of the base we have assumed that is in the positive y direction, okay, y0 direction. So, this is what 0 g 0. Now, I can do this multiplication. So, you have g s1 here, g c1 here, and other term is 0. So, this is what we get. This is essentially the acceleration for the origin of first frame expressed in terms of the first frame. Okay. Then, in order to get CG acceleration of the first link, okay, so CG acceleration of the first link is going to be what? This is the our expression which we have got earlier. Okay. So, this is the expression. So, where CG of the I plus 1th frame is basically the acceleration of the CG of I plus 1th frame is actually acceleration of the I plus 1th frame, plus again you are going to have 2 cross term over here, and there is a 1 cross term involving the angular acceleration of the I plus 1th frame. Okay. So, now if I put I is equal to 0 here, so this is what I get Vc11, and here I have omega 1 derivative expressed in terms of the first frame. This is going to be Pc11, this is omega 11 cross, then you have this term and cross this term plus V11 derivative this term. Okay. Next what we can do is that I can write this as a skew symmetric matrix, okay, and this as a vector. So, this as a vector is this one, okay, because I have already assumed the CG over here, okay. So, you are going to have L1 and this is along the x axis, the link length as per the DS notation, we assume that way. So, this is there and this is written as a skew symmetric matrix. Similarly, this one, this cross is written as a skew symmetric this one, okay, and this cross is again written as a skew symmetric matrix here and this vector over here, okay, and this is what we got from here, okay, this value we have already got. So, I can substitute that over here, okay. And now, when I do the multiplication, this is what I get. Okay. So, we have 0 here, then L1 theta 1 double dot here, 0 here. Okay. There is another simplest way of doing it, and that is this one. You see this angular acceleration is along z direction, right. So, this is the k component will be coming over here. Okay, and this length is along x direction. So, you are going to have the I component. Okay. So, k cross I is actually you are going to get the j. So, this is what we are getting. Okay. The j component I am getting, and here this is the theta 1 double dot this term, and this is your L1 basically. So, this way directly I get. I just showed it here so that you can have feel that how can it could be implemented in a matrix formulation way. Okay. So, this is done. Similarly, here the first term I keep here as it is and I multiply these two. Okay. So, the second one is my L1 theta 1 dot and then this term is as it is. Okay. So, after this then I can do further simplification. Okay. So, I have 1, 2 and 3 terms over here. Okay. This one multiplication will be giving me what? This multiplication will be giving minus L1 theta 1 dot square, right, here in the second term. So, this one is my second term minus L1 theta 1 dot square. This is as it is, this is as it is. So, now I can do the addition minus L1 theta 1 dot square plus GS1 L1 theta 1 double dot plus GC1. Okay. So, this is the acceleration of the center of mass, okay, of the first link, okay, and because of my point mass assumption that center of mass is over here, all right. So, this is we have done. Now, when we have found out the acceleration, now let us find out the inertia forces and inertial moments, okay. So, for that this is the expression we have already seen. Okay, the iterative equation, that is force acting on the I plus 1th link is equal to mass of that one, and this is the acceleration of the CG of that link. Okay. So, put I is equal to 0 here. So, F1 here, M1 here, and this is Vc1 all expressed in terms of the first frame. Okay. So, this value I have just got here. Okay. So, I can simply multiply with M1 to these values, okay, and I will be getting this inertial force acting on the first link and expressed in terms of the first frame. Okay, fine. Similarly, this is the expression for moment propagation, inertial moment here. Okay. So, in this one again you see that you have I omega dot term is coming, then you have omega cross I omega term, this comes as we have seen, and this effectively comes from the Euler equation. Okay. So, let us put I is equal to 0 here. So, N1 1 and this is your omega 1 derivative I1 expressed in terms of C1 frame, here you have omega 1 and here you have I1 expressed in terms of C1 frame, and here this is omega 1 I1. And you see this term we have already assumed to be 0, this term we have already assumed to be 0. So, essentially what we are getting is we are all moment component in the xyz direction, that we are going to get 0 here. Okay. So, that was the outward iteration for the link 1. Okay. So, next, and where what we did, we found out the angular velocity, then we found out the angular acceleration, and then we find out the translational acceleration, and then we found out the translational acceleration of the CG, and then we calculated the your inertial force and the inertial moments. All right. The similar approach we do for the link number 2. Okay, and that I can get by putting I is equal to 1. Okay. So, I can put I is equal to 1 in this equation. So, you have omega 2 here, omega 1 here and theta 2 here, everything expressed in terms of the second frame. Okay. So, that is there. So, this value I can get because I know this equation, right. So, I can put this rotation matrix I is equal to 1. So, I will be getting R1 expressed in terms of the second frame, and this is what it is going to be. Okay. So, now I can come over to this equation omega 2 expressed in terms of second frame. So, this is rotation matrix, this one. Okay. Omega 1 1, this we have already evaluated, and this theta 2 dot is this one. Z2 expressed in terms of second frame essentially means that we have to pick the z component. So, x and y component are going to be 0 here. So, this is the z component. Now, if you do this multiplication, so what you are going to get 0 0, and from here this is what you are going to get theta 1 dot plus theta 2 dot. Okay. And you see this is quite obvious also that second link angular acceleration is going to be the angular acceleration of the first link plus that of the second link. So, physically also it is intuitive. Okay. So, I have intentionally taken this problem so that you can correlate these things with your physical understanding as well. Okay. Next, after finding the angular velocity, now let us look at the angular acceleration equation here. Okay. So, I can again put I is equal to 1 here. So, omega 2 is omega 1, omega 2 derivative is omega 1 derivative, right, plus you have the theta 2 double derivative here, and you have 1 omega cross theta 2 dot term over here, everything expressed in terms of the second frame. Okay, here omega 1 is represented in terms of the frame, its own frame. Okay, so that is 1. All right. Now, we can put up these values. So, this value is this one, this value I can put this one, and then this value again here. This one I can write as a skew symmetric matrix, this one. Okay. And this theta 2 double dot skew symmetric matrix, then you have theta 2 dot. So, this vector column vector, you have the theta 2 double dot. So, this column vector, only the z component being written over here. All right. Now, if I do these multiplications, so this is what I am going to get from here. Okay. You can just check. So, this is what I am going to get, that is 0 0 theta 1 double dot plus theta 2 double dot. And as I said, this is intuitive also. Okay. So, you can just visualize that the angular acceleration of the second link is going to be this one. Okay. Next, let us look at what happens to the translational acceleration of the second frame. Okay. So, we just write the equation for linear acceleration propagation. I put I is equal to 1 here. So, I have this V2 derivative. Okay. So, this is sum of that of the first link frame, okay, acceleration, plus you have this omega cross r term over here, plus omega cross r, double cross terms are coming over here. Okay. And if you look at this expression, then you will see that this part, okay, is nothing but what we have already calculated. Okay. What we have already calculated, that is the acceleration of the CG of the first link. Okay. So, this is what it is, and you see that because of the point mass assumptions, as I said, the origin of the second frame is going to be the same as the origin of the CG of the first link. Okay. So, that is why this is same. So, this value we have already evaluated previously from here. So, that value we have already evaluated previously from here, this one. Okay. So, this value I can directly put it up there. Okay. So, this value I can directly put it over here. Okay. And yeah, and this we already know. Okay. And then we can just do the multiplication. Okay. So, you can just try doing it. So, C2 being multiplied over here, then S2 being multiplied over here, okay, to this term, and here minus S2 being multiplied to these terms over here, and C2 being multiplied to this term over here. So, this is what you are going to get. Okay. And here then we can some simplification. So, let us write the acceleration term first. So, this L1 S2 theta 1 double dot, this is there, then L1 C2 theta 1 dot square. So, this term is there, and here if you look at this equation, okay, so this is sin theta 2 cos theta 1 plus cos theta 2 sin theta 1, which is nothing but sin theta 1 plus 2 basically. Okay, this is sin theta 1 plus theta 2 actually. Okay, so that way I have simplified. And similarly this term over here, then you have the square term over here, and this cos theta 1 cos theta 2 minus sin theta 1 sin theta 2. So, this is cos theta 1 plus theta 2. Okay. So, this is what we can do this simplification. Again, now we have to find out the CG acceleration of the second link. Okay. And this again I can get using this recursive equation which we have seen. So, here I put I is equal to 1. So, you have Vc2 derivative, this omega 2 derivative, and this Pc2 derivative, omega 2 cross omega 2 cross Pc2 here plus V2 to V2 derivative here, all expressed in terms of the second frame. Okay. So, that is there. Now, we have found out this value. Okay. So, this I am writing as the skew symmetric matrix here, and this Pc2 expressed in terms of second frame. So, this is here because my this one is over here, that is the CG of the second link. Because of this point mass assumption, it is at this point. So, that is at L2 here. So, this is how this comes. Then I write these terms. So, it is this term skew symmetric matrix, again this is skew symmetric matrix, and this is this term. Okay. And this V22 derivative is this term basically. Okay. Now, I can do the simplification. Alright. So, with simplification here I have 0, L2 being multiplied over here, then again 0. Here again I can do this simplification. So, this is what I am going to get, and this term I am putting it as it is. Okay. And then I can again write it in this form basically, the double derivative terms I am putting first, L1 S2 theta 1 double dot minus this term L1 C2 theta 1 dot square plus my G term. So, this is G S1 2, and then this one term minus L2 theta 1 dot plus theta 2 dot whole square. So, likewise I can rewrite that second term. So, this way I got the CG velocity of the second link, which is over here. Now, again once we have the linear and angular acceleration, now I can write the Euler equation, the Newton equation for the inertial force, and the Euler equation for the inertial moment. Okay. So, this is the equation which we have already seen for the inertial force calculation in a recursive way. So, if I put I is equal to 1, so this F2 is M2 here, and this is Vc2 derivative over here, all expressed in terms of the second frame. Alright. So, this is what this one value I have just calculated in the previous slide. So, I pick up this value from here and I put it up over here. So, this give me inertial force acting on the link 2 basically, right. Alright. So, this is how I can do that, and then I can do the simplification. Okay. I can do this multiplication by M2 and I can write it like this. Okay. Then the inertial moment, this is the expression. Again here it is a simple Euler equation where you have I alpha term basically plus omega cross I omega term. alright. So, I can put n is equal to 2 here, I is equal to 1 here. So, this is what I get, and again you see that because I am having the point mass assumptions, okay. So, this is going to be a null matrix, this is also a null matrix. So, I am going to get this n2 as 0 0 0. Okay. So, after the outward iteration where we have evaluated the inertial forces and moments, now let us come inward. Okay. So, we do the inward iteration for the last link first, that is the link number 2. This link we do the inward iteration. So, for this is the equation, recursive equation which we have seen in the last lecture. Okay. So, I can put I is equal to 2 here. So, this is F22 is equal to F33 R322 plus F22, right. Again F33, this is 0 because we have already assumed that nothing is acting here. Okay. So, F3 is 0 here and N3 is also 0 here. Okay. So, not acting here. Okay. So, this I can put that. So, my F2 is going to be the same here, okay. So, which we have calculated, and I can pick up this value directly from the previous slide from where we have calculated this one, okay. So, this is what I get, this one, okay. Okay. Then for the moment, this is the moment equation actually, okay. So, here moment acting at the ith link basically. So, this will be what? This is the inertial one, inertial moment which we have just evaluated, and this is moment acting at I plus 1th link plus what? You have this PCI cross Fi term, and then you have a Pi plus 1 cross Fi plus 1 term here, and everything expressed in terms of the ith frame. We have seen all this in detail. So, let us put I is equal to 2 here. So, this is N22, this thing. So, this is what we are going to have, this equation. Now, here you see this we have evaluated to be a null vector, right, in the previous slide here. So, this we have already evaluated null vector, right, and I am assuming that there is nothing acting at the tip, okay, no moment is acting at the tip here, okay. So, this is 0. So, now what I am left with? I am left with this term. So, this term, this one, this PCU2 cross I am writing as a skew symmetric matrix. So, this is what it is, and this F22 is this one which I am substituting here. Again this term is going to be 0 because no force acting here, okay. So, F3 is 0 and similarly N3 is 0, okay. So, that is what, and then I can do this multiplication. Okay. So, if you do this multiplication, this is your 3 by 3 matrix, this is 3 row 1 column. So, essentially what you are going to get is 3 row 1 column here. Okay. So, this first row being multiplied here, so you get 0, this row being multiplied here, so again you get 0, and then this row being multiplied. So, essentially in these terms you will be getting L2 being multiplied here. Okay. In this term your L2 will be getting multiplied. So, what you will be getting M2 L1 L2 C2 theta 1 double dot M2 L1 L2 S2 theta 1 dot square plus M2 L2 G C12 plus M2 L2 square and this one. Okay. And this is again tells us because the moment which is going to act at the joint, that is going to be about z axis. And this is true because we have assumed the planar manipulator where my z axis is perpendicular to the plane, and this joint this is the second one basically. So, this joint is turning about the z axis, that is why you are getting only the z component over here. Then we can have a look at inward iteration for the link 1. Similarly, this is the same equation which we have seen previously. So, I can put I is equal to 1 over here, okay, and I can this F2 we have evaluated, okay. So, that we can get from here R2 1, I can substitute here, and this one F11 we have also evaluated. So, that I can substitute directly over here, okay. And regarding this joint moment here or joint torque, so this is the equation, I can put n is equal to 1 over here, okay. So, this is what I am going to get, and in this equation what this the contribution from first term is naturally this is 0, we have already evaluated that. Okay. So, you have this n22 which we just evaluated here, okay, and R21 this is that term, and then this one I can write as a skew symmetric matrix. So, this one, and F11 we have evaluated. So, it is this vector. Then P21 cross I am writing again as a skew symmetric matrix. So, this one, then you have R21. So, it is this one, and F22 again I get this value from the previous slide. So, I can put it up here. So, again, so with the simplification, so here we have basically 3 terms coming, okay. One is this one, another one this one, and another one this one. So, these 3 terms are this one, first, second, and these are the third term, okay. So, again I can simplify these terms, okay. So, I can write them together. So, first this term is as it is here. The first term I am writing as it is, the second term I am writing as it is, and the third one I am doing this 2 multiplication basically, okay. So, we have 0 0 0 initial one, second one 0 0 0, and in third case you have L1 S2 multiplication going to the first row and L1 C2 multiplication going to the second row, okay. So, this one is there, and then we can simplify that. So, if we do that, then this is that the simplified expression for the third term which comes, this is my first term and this is my second term, okay. And so, this is what I am getting for my N11, okay, and N22 we have already evaluated, alright, we have already evaluated N22. Now, in order to get the joint torque, I extract the Z components, okay. So, for the first joint, okay, so I can extract all these Z components, okay. So, this is that expression, the extracted Z component for the, this is for the first joint and this is for the second joint. Alright, I have done here some color coding just for you to have an understanding which term is coming over here. And again, when we are writing this one, we have followed certain way. Initially, we write the acceleration terms, okay. So, these terms are there, then, okay, and then we have the joint velocity square terms are there, and then you have the theta 1 dot and theta 2 dot term, and then you have the g terms over here. The interpretation of these terms and all that I am going to discuss in the coming lecture, what is physical meaning of these terms, okay, and how these individual terms are contributing to the joint torque. So, that we are going to see in the coming lecture, okay. So, here as I said, I have done some color coding over here. So, for example, as I said, this term is what written over here, okay. So, written over here. So, this is how I have put it, and these 2 terms are combined, this term and this term is combined over here and written it together, okay. So, this I have done intentionally for you to have the better understanding, okay. So, that is why at the beginning of this lecture I asked you that you try to do it by your own hand, then you will be having a feel about how these individual terms are contributing to the joint torque. And as I have told you at the beginning, these joint torque are basically helping us in selecting your motors for a manipulator, okay. So, we will have much more discussion about this one. So, the expression for the torque at the actuator, that is tau 1 and tau 2, which we have just evaluated, these are function of what? All these, the joint position, velocity and acceleration, okay. And this complex nature we have got for the simplest type of manipulator which is possible, that is a 2 degree of freedom planar manipulator. So, think about how these expressions are going to look like for the more complicated case of say 6 degree of freedom manipulator, okay. So, it is naturally going to be very complex, the closed form equation, okay. So, to summarize, The complete algorithm for computing joint torque from the motion of joint is composed of two parts. Okay. In the first part, we calculate the link velocities and accelerations iteratively, okay, beginning from link 1 and we go till the last link, okay, and the Newton-Euler equations are applied for each link to find out the inertial forces and moments, okay. And in the second case, for the given force and torque of interaction at end effector, okay, we calculate the joint actuator torque, okay. Again, that is done recursively, that is from the last link back to the link 1, okay. So, with this, these are the references for your further reading, and I would like to close. Thank you. Happy learning.